Good afternoon. Today we will be covering Objective 3 Alpha, and in 3 Alpha we will be identifying basic facts about principles, capabilities, and limitations of satellite transmit and receive systems. As an RF transmission systems technician, you need a basic knowledge of the transmit and receive systems to adequately maintain satellite-based equipment. As an overview, we will be covering the basic radio picture, a few fundamental radio parameters, radio performance assessment, and lastly, some ancillary functions. This is our picture of a basic radio, just to give you a little bit of a visual representation. I don't know if you all got this in a packet. Typically, this is something that I would hand out with your C's and D's and the radio horizon comparisons. I don't know if you guys got this in a packet or not, but we'll be filling this out as we go along and explaining how our signal converts from baseband to IF to RF and then back down to baseband on the receiving end. So your top row is your transmit components, and then your bottom row will be your receiving components. And then we'll go into a little bit about what each one of those does for our signal, how it changes it, what it does to it, etc. Our first point will be the basic radio picture, and we are specifically going to focus on the transmit path right now, which the overall objective is to transmit our composite baseband signal to our distant end. We accomplish this in 3 different steps, where we will modulate the baseband to a 70 megahertz IF signal, and then upconvert it to our final RF frequency. And then lastly, before it leaves our antenna, we'll apply amplification to our RF signal so that it can make it to where we're trying to send to our distant end. Our first component in the transmit path, after it leaves our multiplexer, where you have the aggregate baseband output, will be our modulator. And our modulator converts, or as it says, modulates the digital baseband to an intermediate frequency, normally 70 or 700 megahertz. So for the sake of this block though, I would stress trying to recall and remember 70 megahertz IF. You'll see that pretty consistently throughout block 7. But it has the capability of modulating that baseband signal into a couple of different IF frequencies. So after we've modulated our baseband signal, we will then upconvert the IF output to the selected transmit RF, and what that means is you as the user have the ability to manipulate the frequency settings on your upconverter to determine what RF is generated coming out of this specific component. So your IF frequency, which is typically resonating at around 70 megahertz IF, will come into your upconverter, and then what happens is there's a local oscillator frequency that is input into a sum mixer. I'm sure y'all have probably heard of that, like from block 2, you had your sum mixer and your difference mixers. But your sum mixer will then combine the local oscillator frequency with the IF frequency to generate the RF out. So whatever you've designated that RF frequency to come out of your upconverter as is what the upconverter will output. So like for instance, the Tisser range, it would upconvert it to between 14.4 to 15.25 gigahertz, which is in the super high frequency range. But that's just an example of what the upconverter would do. It would take that 70 megahertz IF and create a frequency range that fell in between 14.4 to 15.25 gig. So after your final RF frequency has been achieved, the output will then go through your high power amplifier, which essentially just provides amplification. It just provides power to your signal and boosts it so that when it leaves your antenna, depending on how far you have to go, it can actually reach your distant end. Because y'all have talked a little bit about radio wave propagation and how there's a little bit of a fall off after it travels a certain distance, right? And the signal gets weaker. Y'all know what I'm talking about?
Yes, sir.
Okay.
Yes, sir.
Yeah, so the HPA's job is to make sure that your RF signal is boosted enough so that when it leaves your antenna, it has enough power and strength to be able to get to where it needs to go. Does anybody have any questions on the transmit path before we start the receive?
Is there a reason it's 70 or 700 and nothing in between?
So those radio parameters are specifically designated most likely by the companies that have created this equipment and being able to determine its tolerance and how these things are specifically tuned. So there's some kind of threshold that designates whether or not you're operating at 70 or 700. It's all based on the equipment parameters that you have of whatever it is that you're working. Does that make sense?
Yes, sir. Thank you.
Oh, yeah, no problem. So in our receive path, now that we've transmitted the baseband, which is the objective of the transmit path, the objective of the receive path is then to recover the baseband. So we started off as baseband, we have to end as baseband. This is accomplished in 3 steps again. You're going to recover your RF signal, then down convert your RF back to IF, and then your IF will then be demodulated into a baseband output before it goes to your demultiplexer for dissemination to your distant end users. Your low noise amplifier has to be capable of 2 things. It has to have a high degree of sensitivity and has to be able to provide amplification. So it has to have a high degree of sensitivity and selectivity in order to be able to differentiate between the noise and distortion that is inherent in distant transmissions, to be able to pick out the specific RF signal that you have this programmed to. So your LNA is going to be programmed to receive whatever your transmit frequency was at your transmit end. And then the LNA's job is to eliminate the noise that is inherent with the transmission and then amplify the specific RF signal that we're looking for. After you've received your RF into your LNA, it then amplifies it, outputs it to your down converter, and your down converter's job is to take the incoming RF signal and down convert it to IF. So it's whatever your receive frequency is set at, and then there's a difference mixer in this one. So your local oscillator frequency is resonating at whatever it's designated to resonate at in order to strip that local oscillator frequency from the incoming RF in order to generate a 70 megahertz IF out. After we've down converted that RF signal to an IF signal, the IF signal is then received by your demodulator, which converts or demodulates your IF frequency back down to baseband. And your automatic gain control circuit provides constant output. So does anybody remember what, or have you ever talked about what automatic gain control represents? Anyone?
Yes, sir.
You have? What do you recall about automatic gain control? Just in your own words, there is no right or wrong answer. Like, we're going to talk about it. It's not a huge deal. I'm not going to put you on blast for giving a partially correct answer or anything like that here.
Sure. Doesn't it control like the amplitude or something?
Right. So it's the gain applied to your signal across a circuit or cable run, and it's all based on how strong or weak your signal is being interpreted by that circuitry. So if your signal is weak, automatic gain control will boost it. But if your signal is coming in too strong, it takes power out of it so that it doesn't fry your circuitry where it has to go through. Does that make sense? So it's just like an automatically occurring form of gain control. AGC. Does that make sense to everybody?
Yes,
Makes
sir.
sense to me.
Cool. And there we go. There's our complete basic radio picture. We've filled in all the blanks. So again, just to reiterate, here on the left, can you all see my pointer on the slide?
Yes, sir.
Okay, so right here on the left, where you see those red arrows coming in, we've already discussed the multiplexers concerning the NSM and how that information comes in and then leaves on the distant end, conversely. So coming into your multiplexer, you have these red arrows. Those are all of your user inputs. Your multiplexer then takes those user inputs and combines them for transfer across an aggregate interface, which then goes into your modulator or your modem. And that modulator takes your incoming baseband signal, leaving your MUX, and turns it or modulates it into a 70 or 700 megahertz IF out, which is then received by your upconverter. And your upconverter takes your 70 megahertz or 700 megahertz IF, combines it with the local oscillator frequency inside that component to generate a final RF out after it leaves, amplified by the HPA. And then on your distant end, after the signal is sent out of your antenna, your LNA will then pick out that specific RF frequency amongst all the noise and distortion, amplify it, transmit it to your down converter. Your down converter takes the incoming RF, strips the local oscillator frequency that is resonating inside of it to generate a 70 or 700 megahertz IF out, depending on whatever your equipment is designated to generate. And then your modulator, or demodulator rather, or your modem, again, on your receive end, takes the 70 megahertz or 700 megahertz IF, demodulates it back down to a baseband signal, so we've successfully recovered the baseband on the receive. And then your demultiplexer demultiplexes the incoming baseband signal to disseminate it to all of your users here on the receive side, where the black arrows are coming. Any questions on this before we press?
No, sir.
Okay. And this is just a little more in-depth with the extra steps as far as where things occur and why and what components are at work here. So this is how I described to you. Your modulator combines IF out, upconverter takes the IF, introduces this as a local oscillator right here. That's what that little sine wave inside the circle represents. And it's combined in the upconverter, sent to your HPA, amplified out. I'm not going to beat this horse to death, y'all. I think I've said this one enough, but everybody gets the gist of this process, right?
Yes, sir.
So this is something that wasn't covered in the basic radio picture that we saw before. Your branch assembly, otherwise known as your waveguide. So this is your specific component that is attached to your antenna the majority of the time. And whenever we're in block 7, I like to actually be able to take y'all outside. If block 9's not busy doing labs and transmitting on their GMTs, I like to actually go out there and take you to the antennas and show you what this waveguide looks like. But there's specific components that are housed or contained within the waveguide or branch assembly that have a job in honing, filtering, and directing your signal so that it leaves and enters your antenna the way that it should, and your equipment associated with your antenna. And we're going to talk a little bit about what each of these components does for our signal here in just a second. Branch assembly's overall job is to direct microwave energy to and from the antenna waveguide, like I was just telling y'all about. It is also responsible for suppressing unwanted harmonics and external noise. So if you have any kind of RF equipment or anything that's producing some kind of EMI that's around your antenna that's sending your signal, this waveguide or branch assembly's job is to also kind of block out all of that spurious noise that's occurring around it. It also aids in receiver selectivity and permits monitoring of the output power. You can actually create depending on what kind of waveguide you're working with, majority of the time there's a sample point that's created. So I don't know if y'all remember those, the T couplers that you have in block 2 is usually like the best reference that I can give. Does anybody remember those? There's those little couplers that look like the letter T that have all of your cable runs connected to it so you can create sample points for your test equipment. So there's a similar test point coming from your waveguide the majority of the time that you can use to measure, troubleshoot the signal at that point in the transmission on the transmit and receive without interfering with the actual transmission data. Your isolators in your branch assembly will provide the one-way signal flow to prevent reflected energy from damaging your equipment, and also provides impedance matching when transitioning between different media. So, does anybody remember what impedance matching?
Isn't it matching the supply of power?
Yes. So it's making sure that there's no reflected energy and that there's nothing coming back onto the cable that you're transitioning from one to the other. Especially if you're swapping to a different type of transmission medium, i.e., like it says here, the coaxial cable to a waveguide, so those aren't made of the same material, but this provides power matching so that whenever you're transitioning between those two mediums, there won't be any issues. The next component in our waveguide assembly is the directional coupler, which is a physical piece of equipment. And this is where I was telling you the sample point is created for performance monitoring. So it couples your microwave energy to your antenna and provides sample points. Your filter is just like any other filter that you've encountered in your time here in this course. It is tuned to only pass your desired frequencies and block out everything else. Lastly, your circulator, which allows for transmit and receive to occur on the same path without interference. There's two different types. You have your diplexer and your duplexer. Can anybody tell me the difference between a diplexer and a duplex? Anybody want to take a crack at it?
One splits frequencies and the other combines them.
Close. So y'all have heard of full duplex, half duplex, and simplex, right?
Sir.
So your diplexers,
Yes, sir.
your diplexer's job is to be kind of like a traffic cop, right? So you can either transmit or receive. So if your equipment uses a diplexer in its circulator, the diplexer is responsible for saying, all right, are we transmitting or receiving right now? Transmitting, cool. Transmit, but we're shutting off this receive circuitry in the meantime so that transmission can occur. And then after our data transmission is sent and we're then required to receive, it does the inverse. So it'll shut off the transmit circuitry so that the receive circuitry is open for reception of that transmission from your distant end. Whereas a duplexer is what the definition just in that bullet point above where it says allows for transmit and receive to share the same path. A duplexer allows full duplex to occur, so you can have transmit and receive happening simultaneously without them interfering with each other. Now that we've talked about that, does everybody understand the difference between diplexers and duplexers?
Yes, sir. Can you explain diplexer one more time?
Yes, I can, absolutely. Your diplexer is like a traffic cop. So if you have a circulator that is considered a diplexer or is classified as a diplexer, then it will only allow transmit to occur at one point, and then your receive circuitry, it will then shut that off so that your data transmission, when you're in transmit and actually sending information, can occur without interference. But then after your data transmission is sent and you then need to receive, it will shut that transmit circuitry off so that your receive circuitry can be open for reception of that transmission. Does that make sense?
Oh, okay, I see now.
Like an electronic airlock or something?
Yeah, pretty close. Yep, absolutely. So then, but then your duplexer allows for both of those things to happen at once, regardless, and they don't interfere with each other because it's allowing transmit and receive to occur on the same path. Did that clear up your question?
Yes, sir.
Perfect. All right, now, does anybody have any question about the branch assembly before we talk about Rago? Okay. Your automatic gain control, which we talked a little bit about AGC earlier, exists to ensure a constant output. So if it's high, it'll draw it back, and if it's low, it'll amplify it. Your receive signal level and your automatic gain control voltage are always going to be directly proportional, whereas your receive signal level and gain will be inversely proportional. And this is because we want to make sure that our output always remains constant. So these are all related to each other in the way that they are to make sure that, lastly, our output is always the same. So if y'all haven't talked about receive signal level at any point in this block yet, have you? Anyone?
No, sir, we have not.
Okay, because I know it's highlighted in the TISR TO, and whenever you start talking about the TISR specifically and we start digging into the C's and D's, it clarifies and expands upon receive signal level and its importance at that point. But just to give you a little bit of insight, your receive signal level is a reading that is generated from a sample point on your receive equipment in being able to tell you how well you're receiving the transmission from your distant end. So based on those things is how the others would react or occur, if that makes sense. Yes?
Yes, sir.
Clear as mud?
Yes, it is for me.
But like I said though, we'll talk about that a little bit more and kind of expand on that later on down the road once we start digging into the C's and D's for the TISR. So just don't sweat it. But just you need to remember that RSL and AGC are directly proportional. RSL and gain are always inversely proportional, and your output will remain constant. All right, fundamental radio parameters kind of coming up on the end here of this objective. We'll be covering your frequency accuracy and stability, bandwidth and what that means to us, frequency response, your selectivity. We've talked about that a little bit whenever we were discussing the LNA, gain, which applies to both your LNA and your HPA, and then your sensitivity, which again applies to your LNA. Because remember I told you that it has to have a high degree of selectivity and sensitivity. And this is going to clear up a little bit why those things are important and hopefully make a little bit more sense as to why those two things are important within your low noise amplifier. Your frequency accuracy and stability all depend on the quality of your oscillator that is used. We talked a little bit before, or y'all talked a little bit before with Mr. Mayer in the previous objectives, the quality of different types of time sources, so your quartz oscillators and your atomic oscillators, and how those differentiate, yes?
Yes.
Okay. And then you should have talked about how quartz oscillators are less efficient than atomic oscillators because they're affected by the piezoelectric effect, which we can control the temperature of those quartz oscillators, but not the aging, because that is something that is inherent to that piezoelectric effect, and just over time your quartz oscillators will degrade. But then your atomic oscillators, just count the oscillations of highly stable atoms within the oscillators being used, and then that's what creates your time. But your frequency accuracy, how accurate of a clock your radio is providing, and the stability of your transmission is determined and dependent on the quality of your oscillator. Your bandwidth is the difference between your upper and lower frequencies at which the radio is designed to operate. To note, before, we should have already discussed at an objective in this block where bandwidth can be considered a couple of things. At the general multiplexing terms, I believe, is the objective where it was taught, where it's considered either a fixed rate or a range of frequency. You all remember that?
Yes, sir.
Okay. So then, like, when you're talking about a fixed rate, like with the NSM50, each type of port, your NRZ, your CDI, your T1E1, and your HISI ports all have a fixed rate or speed that each port provides. So like your fixed rate for your HISI would be a 52 meg. That's considered the bandwidth of that port because it can facilitate up to a 52 megabit connection. But with a radio, it's different because at this point, we're not worried about data rates. We're talking about range of frequencies because we're talking about the RF spectrum frequency bands that we're operating in, etc. So your bandwidth in a radio is the difference between the upper and lower frequency. So again, like for the TISR, 14.4 to 15.5 gig, which is in the super high frequency. And then you have your frequency response, the frequency range over which an audio device or system will produce or reproduce a signal within a certain tolerance. So it's the quality, so how well the radio is sending and receiving the data or information. How viable is that response in the way that you're sending the data to your distant end. And then you have your selectivity, which this pertains to the LNA, is the ability to process desired frequencies and reject the undesired ones. So anything that we don't want gets filtered out. And if your piece of equipment or your component is capable of doing that and can do it well, that means that it has a high degree of selectivity. And then to cover the last couple, we have your gain, which is considered a value of amplification that a signal obtains in passage through an amplifying stage or system. So like I said before, whenever we were covering the main points of the fundamental radio parameters, your gain's applied in your HPA, and not only in your HPA, but then again in your LNA. And lastly, your sensitivity, which applies to the low noise amplifier again, is your receiver's ability to distinguish between low-level signals and noise. So based on the definition for your selectivity and your sensitivity, does that make more sense to y'all as to why I said that your LNA has to have a high degree of both of those?
Yes, sir.
Cool. Yeah, usually whenever we go into actually defining the fundamental radio parameters and what those words mean to us, because we start talking about them a little earlier on in the objective, it starts to make a little more sense as we are able to expand upon it. Does anybody have any questions on the points that were covered before we press?
No, sir.
not yet.
No, sir.
Okay. So in a radio performance assessment, your system's approach typically occurs as an end-to-end test that analyzes an entire network to identify problems prior to system failure. That second bullet point I like to highlight may result in coordinated troubleshooting between multiple sides of your network. So in your end-to-end testing, so say we're trying to send a data transmission to Langley, where I was telling y'all before that I was stationed, and something on my side of the network isn't working. Well, then you'd be able to call your distant end and do a couple of things. So then they can determine whether or not they're even able to see or receive your signal from point to point and where you're sending your data transmission. And based on that information, well, man, if they can't even see us, that could only be a couple of things. And then you would use your technical order associated with whatever antenna or radio that you're operating to figure out if your transmit and receive frequencies are correct. Are you applying enough power to your signal? Is your radio transmitting at all? Honestly, like that right there has been one of the biggest oofs, I guess, as you guys would call it nowadays, that I've ever seen when it comes to trying to talk to your distant end. People don't even have the radio and transmit. So then your data transmission has nowhere to go. So if your transmit circuitry doesn't know to send that information, audio, email, messaging, whatever it is that you're sending, it's just going to stay at your terminal and it's not going to go anywhere. So then that, through your troubleshooting with multiple sides of your network, you would be able to figure out and hone in on whatever component or setting it is that's making your transmission inoperable. And a couple of the performance measures that we'll talk about are your quality, reliability, and speed. Your speed, like bandwidth, has a couple of things that it defines. The quality of your signal is how closely your output resembles your input. The reliability is the percentage of time that the system is available. Then your speed is how fast the system can process data. So what's the fastest speed or data rate that your system is capable of? How quickly can it send and receive that information? And then also, how quickly can you set it up? The antenna, the radio, and make comms. Does anybody have any questions before we press to ancillary functions?
No, sir.
Okay. So in your ancillary functions, we'll cover switching and auxiliary channel, performance monitors, and then fault indicators. Switching, so you'll see switching, and we'll talk a little bit more about this as we move on into the TISR portion of this block, but switching is used for redundancy, and it can switch standby equipment online. Now, when we're talking about switching as it pertains to the TISR, it's more about when we're transitioning from our loopback mode and performing our loopback testing, and then switching to actually transmitting and operate and sending audio to our distant end. But this is also pertaining to switching on to standby equipment, as it says in our bullet point here, in relation to many systems having equipment in standby that have multiple copies of. So for instance, in the fixed SATCOM terminal that I was responsible for maintaining at my last base, we had 5 paths of communication. And what I mean by that is we had 5 multiplexers, we had 5 modulators, we had 5 up converters, and we had 5 HPAs that were all in tune, in line with each other, so that if one path went down and we lost a data transmission, in an effort to get that data transmission back up, we could just switch our standby equipment on immediately and start transmitting on that separate path. Because all you have to do is go in and configure your up converters and your modulators and all of your equipment that's associated with that path that went down, and you can just switch that standby equipment online to make sure that there's no mission downtime. Then your performance monitors allow for troubleshooting and maintenance before performance degrades, measures between the upper and lower limits or thresholds. So this performance monitors, what would fall into your performance monitor category would be like your bit error rate test set and performing loopback function. So you perform loopbacks on your systems in order to make sure that all of your equipment is within tolerance and that it can send a signal from one point to another on your transmit and receive. Because if you're doing loopbacks, and loopbacks are crucial, because if you're doing a loopback on your system and you identify there's an issue and where the signal is not able to process correctly somewhere in your transmission path as signal flows, then you're not going to be able to transmit anything to your distant end anyways. So we have those performance monitors to make sure that our equipment's working the way that it's designed to. And so if we identify that the equipment is not, then we can remove and replace or take it apart to fix it and then get it back running on the rack or what have you. But performance monitors are crucial. And then you have your fault indicators, which usually go in hand with those performance monitors because they're represented by visual and audible alarms. So with the pisser, whenever y'all are doing the labs, you will have a fault indicator that you can see, which is the error light that's on the front of your baseband assembly, and it usually flashes at it's identified as a 2.7 kHz rate. But if it goes solid when you're doing your loopback test, that means that there's something wrong. Like you set up the transmit or the receive signal incorrectly, you're applying too much gain, something to that effect. But these things are important because, as it says in the slide, it aids in troubleshooting, and that's supposed to be facilitates, not facilities. That's a funny typo, facilities. But this aids in troubleshooting and facilitates maintenance. So it lets us know if something's broken or if we need to fix it, something to that effect. All right. In Objective 3 Alpha, we discussed the basic radio picture, how our transmit path's responsibility is to transmit the baseband signal, and then on our receive, we will then recover that baseband signal. We talked about a few different fundamental radio parameters, as well as radio performance assessment and why that's crucial to our job. And then lastly, some ancillary function. Before we wrap up 3 Alpha, does anybody have any questions on any of the topics that were discussed? Objective.
No, sir.
Okay. In Objective 3 Bravo, we will be identifying basic facts about principles, capabilities, and limitations of modems. As RF transmission systems technicians, communications across a network will require knowledge of many devices such as modems. In 3 Bravo, we will be discussing general modem principles, different types of modulation, forward error correction, interleaving, which is a type of forward error correction. We'll identify some traditional based modems, and then lastly, IP based modems. To begin, we'll be talking about a few general modem principles. A modem, by definition, is used to modulate an analog carrier to encode digital input data, and then also to demodulate the incoming carrier to decode your transmitted information. I know we've covered a couple of different things that have a few different definitions. Baud is also one of those things. So baud can either be classified as your baud rate or your symbol rate. But regardless of what you call it, either your baud rate or your symbol rate, this determines the speed of the bandwidth per second. Typically as it pertains to your modulation types, which whenever you see that we're discussing the different types of modulation in the modems, it will have a baud rate, like 1 bit per symbol is usually the way that it spells it out. So how many bits of information or data that can be transmitted per second. Then our different types of modulation. Modulating an analog carrier signal has 3 basic components. It will either alternate in frequency, amplitude, or phase. And that affects our signal in different ways. Let's discuss those things. So in your frequency shift keying, you're going to alternate in frequency only. One frequency for logic 1s, and then there's a secondary for your logic 0s. This is what I was talking about before. FSK is represented by using 1 bit per symbol. And then your amplitude shift keying, you're going to alternate in amplitude only. Again, this one uses 1 bit per symbol. These are all just visual representations of the frequency shift keying and the amplitude shift keying waveforms. And y'all have access to these slides by chance?
Yes, sir.
Yes, sir.
You do so, yeah. So this is if this is something that you're interested in going back and looking at, feel free. I just like to highlight on the actual definitions and explaining things a little bit better. But if you'd like to go back while I'm discussing these things, watch the video, have the slides up so that you can look at it and then figure out how that pertains to each other. Or if you have any questions about those things later on and you'd like for me to expand on them, please feel free to reach out to me, okay? Then your phase shift keying, there are 2 different types that we'll talk about here in block 7. You have your binary phase shift keying and then your quadrature phase shift keying. Binary phase shift keying alternates in phase only if your logic state changes. So if you have a 0-degree phase shift, so that now we're talking about phase shift and then being out of phase with each other. So this would be where, you know how we were talking about in a balanced transmission line, the transmission on each line have to be 180 degrees out of phase with one another so that there's no interference. So this is kind of expanding upon that concept in that BPSK will only alternate if your logic state changes. So if you have a 0-degree phase shift, which means that there's no change, logic 1 follows a 1, logic 0 follows a 0. But then that will be considered the inverse if you have a 180-degree phase shift. Logic 0 follows a 1, etc. And this type of modulation also uses 1 bit per symbol. In your quadrature phase shift keying, we're getting up a little bit better, your more efficient transmissions now. This transmits 2 bits per symbol, and quadrature phase shift keying is also considered a precursor to quadrature amplitude modulation. Our last type of modulation that we'll talk about. Your quadrature amplitude modulation transmits 3 bits per symbol, up to as many as 10 a day. Which I actually think that there are some systems now that have exceeded that even. So this is just understand that this is your most efficient type of modulation that we talk about in block 7. Transmits as many as 3 to 10. Does anybody have any questions on the different types of modulation before we proceed to forward error correction?
No, sir.
Trying to check the classroom chat as well on my phone. Actually typing anything. If everybody has mics. Go down to forward error correction. Forward error correction is the distant ends modem's job to perform. Forward error correction is accomplished by using multiple copies of the same transmitted message to correct for data errors. So it's expensive due to the amount of storage. So it says expensive because of the equipment that is needed to apply forward error correction to your transmission, if that makes sense to everybody. So forward error correction takes, when it says it takes multiple copies, so if you are using forward error correction in your data transmission, your distant end receives that data transmission, and then if there's a block of data that's missing, it will continue to receive that same transmission until it can extrapolate that block of data to fill in the blank and create the most accurate output message for you to see. And in forward error correction, we have a couple of different forward error correction rates that we talk about. But the most important thing to highlight here is that your first bit, regardless of whatever type of forward error correction rate that you are using, your first bit, so in this one would be the 1, indicates how many bits of data are going to occur in your forward error correction before that bit of correction occurs. So in a 1/2, you'll have 1 bit of data and then the next one's for correction. But in 3/4, you have 3 bits of data that are received and then your fourth one provides the correction. And then your overall system, there's that word again, baud rate, symbol rate, is impacted by 3 different things. Your data rate, so how much information your system can process. Your modulation type, which that's talking about your frequency shift keying, amplitude shift keying, binary phase shift keying, SK or QAM. And then how many bits per symbol, are associated with that type of modulation. So how many bits of data are transmitted per second. And then your forward error correction factor, which is that we were just talking about. How many bits of data are received before your correction occurs. And then combine those, create your overall system speed, essentially. And this is just the information that I was just talking about. So your overall system rate determined by your data rate, so how quick everything happens, how many bits of data are transmitted before your correction bit, and then what type of modulation are you. Does anybody have any questions about forward error correction before we cover interleaving? Okay. Interleaving is one form of forward error correction. This is done by mixing data using time division to correct for errors. Only a bit from a block is lost, rather than a whole block of data. So with normal forward error correction, like I was telling you before, when an entire block of data is lost, it continues to receive the transmission until it can fix it. But it's more information that's lost in typical forward error correction. But with interleaving, because we're using time division instead, anytime we lose information, it's only a bit versus an entire block. So it's just less information, it's more efficient. First, we'll be covering a couple of different traditional modems, and then we'll be covering the IP-based modems. So in our traditional modem types, we have the telephone modem, which is used in tandem with the POTS, such as the 56K dial-up modem. Is anybody in here old enough to remember the what was it? The AOL Instant Messenger, like the AOL dial-up tones? Anyone?
Burr.
Oh my gosh.
There.
I wish I had that link on hand. I think it's in like a different classroom chat, but yeah, that's that sound is like forever ingrained into my brain. Anytime
Maker, were you even born during that time?
No, I'm a little too young for that. 98, that's when I was born, so wasn't really doing much back then.
That's DSL and dial-up were obsolete at that point. But did you? Yep, there it is. Did you just go find it in another class's chat, or did you just look it up on YouTube?
I just looked it up on YouTube, sir.
That's so funny. That's the exact same link that Mr. Mayer uses and posts in his classroom chats. Funny. Yeah, it's anytime I hear dial-up or I read dial-up, I always think of that sound. It's just makes my skin crawl. Okay, so you won't see very many of those plain old telephone systems around anymore. We typically use voice over IP now. So we're going to have power over Ethernet, whereas that's concerned, and then your VoIP phone will be almost like a bridge for your Ethernet connection from the wall mount to your actual desktop or your setup where you have your laptop in the docking station and everything like that. And then we'll start talking about the satellite modems, which are used for communications outside of a deployed location for tactical and strategic situations through a satellite. So you can use a satellite modem to set up a SATCOM shot in the middle of nowhere, as long as you know where you need to point your antenna, and create a secure internet connection so that you can send or receive transmissions from people that you need to communicate with while you're in the field. So your traditional modem types, your fiber optic modem, it's capable of processing extremely high data rates. This is something that's going to be used in today's data transmissions for like most of your data that is facilitated through your internet service providers. You're using some kind of fiber optic modem because you have speeds of up to like, I think 3G is what we're up to right now for commercial internet that you can get at home. I think that's what one of my friends was telling me. He had like a freaking 3G down connection at his house. But these fiber optic...
nearby, sir?
Say again?
Is he nearby, sir?
No. He was stationed actually in Virginia the last time that I talked to him, and he said that he was running like a 3 gig. Insane. That's like, why do you? I don't know. I guess for reasons. I don't know. Like a 3 gig connection, so fast. No, and he's terrible at video games. That's the thing. That's like, it confuses me. I'm just like, I don't understand. He's like, oh, I gotta have that secure connection and know what those lag skips and everything like that. I'm like, man, you're not even that good to be.
Now he has no excuse, sir.
Yeah, right.
It's for Fortnite.
Oh my god, you know what? That's actually not inaccurate. He does play a lot of Fortnite. Ugh.
Oh no, sir.
Yeah, that's no bueno. Okay, so we have 5 stages in our fiber optic modem. First, we have our modulator, then the transmitter, receiver, filter, and then lastly, our demodulator. And in any fiber optic modem, those 5 stages will be constant. So that's something that, remember, whenever talking about fiber optic modem, those are the 5 stages associated with the data transmission and reception. Your IP-based modems, excuse me, I had to burp, apologize. Your IP-based modems access the internet differently than your traditional modems because they're considered always on. So this means instead of having to dial up, request access, and then be granted access to your ISP's servers, which is what you had to do with a dial-up connection, your IP-based modems will always provide internet to you at your fingertips, ready to go. So like that's just the basic concept of Wi-Fi essentially. So like if you've ever walked in anybody's house and you're like, hey man, I don't really have good reception out here, my 4G mobile data isn't working or whatever, can I get your Wi-Fi password? And then as soon as you plug in that Wi-Fi password and your connection's established and you've been listed as like a trusted user on that network, you can automatically just start surfing the web, right? Yes?
Yes, sir.
Right, so that's the concept behind the IP-based modems, is that they're always on. And then it's not like a, hey, I need to get on the internet. All right, cool, here's the internet. All right, you haven't been on for long enough? Server timeout. You don't get to be on the internet anymore. It's just always available. And then your iDirect modems, these are your high-performance, secure, and portable systems that allow transfer of voice, video, and data across your satellite networks. So these are the modems that we use today. We actually wrote a couple of training products for these over at my last job at QFlight. Your iDirect modems are being used in today's SATCOM networks that we have today. These iDirect modems use time division multiple access in order to create those secure connections. And they multiplex 30 terminals, so 30 user terminals onto just 4 carriers, whereas in frequency division multiple access, so if you were trying to use FDMA in an iDirect modem, you would need for the same 30 terminals, you need more than 10 times the amount of carriers. So the TDMA is just a more efficient form of multiple access for our iDirect modems to use. And then with the operating frequency bands, I always tell my students this, and a lot of them have told me that it's super difficult to remember because it's kind of cringy to say out loud. So if you're ever confused, like if, oh man, I can't remember what the frequency bands are for the iDirect modems, how am I supposed to remember those things? It's CX KUKA. Did anybody just get secondhand embarrassment? CX KUKA.
That wasn't that bad, sir.
Oh, I don't know. It's pretty bad. It makes me kind of, but that's been. I remember memorizing those bands from whenever I was in tech school that way, and I'm pretty sure that's the same way that Mr. Miller teaches it, and that's why I remember it so well. But the iDirect modems also optimize your TCP over IP protocol and traffic via the satellite connections, has a throughput of the 4.2 megabits uplink, and if you're using a single user, your downlink is then increased to 18 meg. And I've never actually interfaced with this SCPC software, so I can't really expand on that. If you wanted to try and go do your own research as to what this pertains to, you can, but I've never actually interfaced with this SCPC software to be able to tell you what the single channel per carrier software is. But 4 bands, CX KUKA, throughput of 4.2 meg, downlink if a single user to 18 meg. This concludes our coverage of Objective 3 Bravo. We discussed some general modem principles, talked about the 5 different types of modulation concerning this block, forward error correction, and how that pertains to our receive equipment and is the receive end's responsibility to correct the data. Interleaving, which is a more efficient form of forward error correction in that you only lose a bit of data when performing interleaving instead of an entire block. Talked about the few different kinds of traditional based modems and the stages associated with the IP based modem. And then the iDirect modem, frequency bands, throughput, and downlink. Does anybody have any questions on 3 Bravo?
I don't think so.
Okay. And if you go back and you watch these videos and hear us talk about this stuff all over again, and it still doesn't click or make sense, as I've said before, feel free to reach out to me. I'm available between the hours of 08 and 1800. Those are my working hours. But if you message me after that, and I have the opportunity to get back to you, I will try my hardest to get back to you as soon as I possibly can to answer your questions. Because like I said, I want everybody to have an equal opportunity to be able to be successful in this block. And that's my job as your instructor, is to be able to provide you with that information.
Thank you, sir.
Yeah, no problem. Absolutely. I love teaching. But if nobody has anything else on 3 Bravo, we'll go ahead and move on to the next objective. Get this knocked out. Does anybody need to take a quick break or anything like that? Go use the restroom, get some water, something like that? Okay. Let's knock out 4 Alpha. This one's going to be relatively quick, simple, to the point. In Objective 4 Alpha, we will identify basic facts about principles, capabilities, and limitations of line-of-sight radio system. And as an RF transmission systems technician, some missions may require you to set up and maintain line-of-sight communications equipment. As an overview, we will be talking about line-of-sight principles, a couple of different types of repeaters, and then lastly, the limitations of those repeaters. Line of sight is a propagation mode that has no physical obstacles between the transmitting and receiving antennas. So line of sight is exactly that. If you don't have line of sight, if you're operating a line of sight antenna and you do not have line of sight, like you cannot see your distant end, you will not be able to send or receive anything. You have to have a clear shot to wherever it is that you're trying to send that data to if you're using a point-to-point line of sight transmission. This is something that should have been included in the packet with your C's and D's that you received. Did everybody get this already? Are y'all looking for your packet, or did you even get a packet?
I'm looking through it. I don't remember seeing
I
that.
don't think I saw that in our packet. I don't think it's on there.
Oh, that's interesting. Yeah, usually this is included in like the packet of information that you're given whenever you're handed your C's and D's and everything for Block 7. But if y'all have access to your slides, just understand that this is something that's going to be on the packet included with your C's and D's that you receive test day. So this is something that is included on the information that you're given. Obviously, there won't be any notes or anything on it. It's going to be a clean, fresh one. But this is something that will be provided to you. And you also have access to these slides. So if you're ever, oh, hey, I don't remember the true Earth radius and how the optical horizon relates to the true horizon and the distance between those two, then you can always come back and reference this slide or watch the video over and get to this point, right? So your radio horizon is going to extend 15% farther than your optical horizon and approximately 33% more than your true horizon. Radio horizon, optical horizon. Sorry, your radio horizon, and then your optical horizon's here, then your radio. True, rather, sorry. In line of sight, will typically operate on the following parameters. Your range in any line of sight system will typically be somewhere between 20 to 50 miles. Your operating frequency will typically range from 3 to 50 gig. And then your nominal power out will range between 1 to 5 watts. The practical application for line of sight radio would be to replace cable transmissions, and this would be due to terrain and distance. So if your cable run needs to be, 30, 40 miles long, that's not ideal, right? That would be more expensive than just setting up a wireless line of sight transmission. And then if you need to overcome terrain or obstacles, we would then use repeaters, which, as it says in the bullet point, extends your distance of your line of sight transmission beyond the radio horizon. So if we start to reach the limits of what our line of sight radio is capable of giving us, we can use a repeater system to extend that signal to wherever it is that we need it to go. Your repeaters are a basic transmitter and receivers, and they must be capable of performing the following two functions. Every repeater must be capable of performing frequency translation and amplification. So if you have a repeater, the repeater must be able to receive a signal, and if it needs to be in a different band, it should be able to translate that frequency to a different band. And then also, because we're using this repeater to extend the line of sight frequency beyond its typical means, it has to be able to apply amplification or gain to your signal so that it can reach either the next repeater or its final destination. Did you say some of your pages say block 8? That's not good. Interesting. So the four different types of repeaters that we'll discuss are your RF repeater, IF repeater, baseband repeater, and then lastly, your audio repeater. Your RF repeater uses a basic radio design, translates your RF, amplifies the RF. That's it. So it has the fewest amount of steps out of all the repeaters that we'll talk about here today. And because it has the fewest amount of steps in the way that it amplifies and transmits your data transmission is going to apply the largest amount of distortion, because the only thing that it's responsible for doing, as it shows you here in this picture, so your 4400 megahertz signal is received, processed by your LNA into your RF mixer, where this is considered almost like an up converter, right? So you have a mixer and an up converter. It's essentially the same thing. So it takes that incoming 4400 megahertz, injects the 260 megahertz being resonated by your local oscillator frequency to create your RF out, which is now a 4660 meg signal. And then instead of filtering that signal down, taking out distortion, trying to make it exactly what it needs to be, it just amplifies it again and then sends it right back out the next antenna to the next repeater or to your distant end. So because of that, this repeater introduces the largest amount of distortion. So in an IF repeater, we get a little bit more involved now. So it uses a basic radio design, so an LNA to down converter, then an up converter to an HPA. So it translates your RF being received down to your, as you can see here, and I won't be able to highlight it because the lettering's a little off, but if y'all can see me using the cursor right now. So it takes your incoming RF, down converts it, so it strips it, to a 70 megahertz IF specific signal, and then that 70 megahertz signal has gain applied to then be up converted, so it gets sum mixed to generate your final RF out. And then it's pumped back up again before it leaves to your distant end. So because there's a little bit more translation here, as far as the RF to IF and then IF back to RF, it gets cleaned up a little bit along the way because of that conversion process. And since that happens, there is less distortion applied in your IF repeaters versus your RF repeaters. Does that make sense to everyone?
Yes, sir.
Cool. Your baseband repeater also uses a basic radio design. This uses an LNA to a demodulator and then a modulator to an HPA. So there's a couple more steps, further translated, refined, less distortion. It demodulates the receive signal, but baseband repeaters can also be used to drop and insert groups of modulated traffic. So your original transmission coming here from your transmitter is sent through to your repeater system, which at your repeater station, this phone and computer, and I think that's a keyboard. Yeah, it's a keyboard. That just represents your groups of modulated traffic that are being inserted into that repeater system. So it's inserted into the transmission to be transmitted alongside the data that was already existing previously before it entered into your repeaters. And then lastly, of the repeaters, you have your audio repeater, which utilizes a full radio design. So you have multiplexer to the modulator to the up converter to the HPA, and then on the receive you have the LNA to the down converter to the demodulator to the demultiplexer. So it uses a full radio design. So it's the most efficient, but it's also the most expensive. And it's the most expensive because of the equipment, a lot like how we were talking about how forward air correction is expensive. It's expensive because of the equipment that you have to have to be able to use that. So in order to be able to use an audio repeater, because it has a full radio design, it's expensive because there's more equipment. Does that make sense to everybody? There's just more parts. There's more pieces of equipment that you have to purchase or have in that suite of the repeater design in order to be able to make it work the way that you want it to. That's why it's costly. And of the limitations of repeaters, there are a few. We have your distance. So if there's a limit, the limitation of the repeater being distance. So if their distance between your two repeaters is too far, you can start to encounter issues. And then it's also based on the amount of like it says, equipment capability. So is that repeater capable of translating your frequency to whatever you need it to go be at the next repeater? Can it apply enough gain to get it to where it needs to go? And then when it says terrain, that means like, are there any obstacles that are in between your two repeaters in your repeater system? Is it overcast? Are there trees obstructing your shot? Things of that nature. And then your needs of the network. So just depending on what kind of transmission needs to be achieved, are your repeaters capable of facilitating that? And then that's why that can be considered a limitation. So then whenever we're talking about noise factor in frequency division multiplexing, you can have 8 consecutive repeater links, so from one repeater to the next repeater. That can occur 8 times using FDM, so you can have 8 hops essentially, before noise starts to get introduced to your signal or your data transmission. But if you're using time division multiplexing, you can have 15 of those links occurring before you have to start worrying about noise being a factor. So in 4 alpha, we discussed the line of sight principles, repeaters, what those repeaters need to be capable of, and then lastly, what the limitations of them are. Does anybody have any questions about 4 alpha?
No, sir.
I know this is a lot of information and this stuff is really involved, and there's a lot of like terms and things like that that we're talking about here. But nobody has anything that they were like scratching their head on, doesn't make sense to them, or anything that we need to talk about right now.
Not really, sir. I think I'll have more questions when I go back over it myself.
Sure.
Same.
Easy enough. And tomorrow we're going to be doing 2 lecture times. We're going to have a 9 a.m. and a 1300. So today we just had the 1300 because I had some things I needed to get taken care of this morning. But tomorrow we're going to have 2 lecture times like y'all are used to, where at the 09 we'll be covering the homework from the objectives that we covered today, and then also answering any questions about the content that was covered today that you may be confused about. So that would be the time to bring those questions to light, is if after we go over the objective reviews tomorrow morning, and make sure that you bring those things to my attention so that we can talk about them, okay? And then at 1300, so we'll break for lunch after our morning review. We'll break for lunch, and then we'll come back again at 1300, and then we'll talk about the objectives for tomorrow.